Hello and welcome. Have you ever looked at the inside of a phone, a computer, or even a simple toy and wondered how it all works? It can seem incredibly complex, but like any language, it all starts with learning the alphabet. In the world of electronics, that alphabet is made up of a few basic components. Today, we're going to learn that alphabet. We'll be looking at this chart of basic circuit elements. These are the fundamental building blocks that engineers and hobbyists use to create every electronic device you can imagine. By the end of this video, you'll be able to look at a circuit diagram and recognize the key players and understand their roles. Let's get started. The first element, and perhaps the most common, is the resistor. You can see its symbol here. It looks like a little zigzag line. The job of a resistor is right in its name. It resists the flow of electricity. Think of electricity flowing through a wire like water flowing through a pipe. A resistor is like making a section of that pipe much narrower. Less water can get through, and the flow is reduced. In an electrical circuit, a resistor limits the flow of current. This is incredibly important for protecting more sensitive components that can be damaged by too much electricity. We measure resistance in a unit called ohms, represented by the Greek letter omega. The higher the ohm value, the more it restricts the flow. In diagrams, you'll often see it labeled with the letter R. Next up, we have the inductor. Its symbol looks like a little coil of wire, which is exactly what it is in real life. An inductor's primary job is to resist changes in the flow of current. Let's go back to our water analogy. Imagine instead of a narrow pipe, you have a heavy water wheel in the middle of your water pipe. When you first turn the water on, the wheel is heavy and takes a while to get spinning. It resists the initial change. But once it's spinning, it has momentum. If you suddenly try to turn the water off, the wheel will want to keep spinning and will continue to push water through for a little while. An inductor does the same thing with electricity. It stores energy in a magnetic field. When current tries to increase, the inductor pushes back. When current tries to decrease, it tries to keep it going. This property makes them essential in power supplies and filters. The unit for inductance is henries, abbreviated with an H, and the component is often labeled with an L in circuit diagrams. To the right of the inductor, we find the capacitor. The symbol for a capacitor shows two parallel lines that don't touch. This is a great visual cue for what it does. A capacitor is like a tiny, rechargeable battery that charges and discharges very quickly. It stores energy in an electric field between its two plates. Think of it as a small water tank with a flexible rubber membrane in the middle. Water can't actually flow through the membrane. This means a capacitor can block a steady, direct flow of current, but it will allow a changing, back and forth flow to pass through. They are used for everything from filtering out electrical noise to timing circuits. We measure its capacity, or capacitance, in a unit called farads, represented by the letter F. In formulas, you'll see it as C. Our last element in the top row is the load resistor. Now, you might be thinking, wait, didn't we already cover the resistor? Yes, we did. A load resistor is simply a resistor that represents the load of the circuit. The load is the part of the circuit that is actually doing the work, like turning electricity into light, heat, or motion. So, if you're building a circuit for an LED light, the LED itself acts as the load. In diagrams, we often draw it as a standard resistor but label it with a subscript L to make it clear that this is the component we're powering. It's still measured in ohms. Now for our second row. First, we have the variable resistor. This is exactly what it sounds like. It's a resistor whose resistance value you can change. Its symbol is a resistor's zigzag with an arrow passing through it, indicating that it's adjustable. Think of it like a faucet on your sink. You can turn the knob to allow a lot of water to flow, just a little trickle, or anything in between. A variable resistor does the same for electricity. Volume knobs on an old radio or dimmer switches for lights are classic examples of variable resistors. They are also measured in ohms. In the middle here, we have a very important component, the battery. This is our power source. Its symbol shows a series of long and short parallel lines. The long line represents the positive terminal, and the short line represents the negative terminal. A battery provides what's called direct current, also known as DC. It's like a water pump that provides a steady, one-way pressure, causing the water to flow continuously in a single direction. It provides the push, or voltage, that makes the electricity move through the circuit. The unit for this electrical pressure is volts, represented by V. Next, we have the variable capacitor. Just like the variable resistor, this is a capacitor whose capacitance can be changed. The symbol is a capacitor with an arrow through it. By changing the capacitance, you can change the resonant frequency of a circuit. The most classic example of this is the tuning knob on an old AM/FM radio. When you turn that knob, you're actually adjusting a variable capacitor, which allows you to tune into the specific frequency of the radio station you want to hear. Like a standard capacitor, its capacitance is measured in farads. And here we have another type of power source, the sinusoidal voltage source, also known as an AC source. Its symbol is a circle with a wavy line inside. This wavy line perfectly represents what it does. Unlike a battery, this source provides alternating current, also known as AC. Instead of pushing in one direction, an AC source is like a pump that constantly pushes and pulls, causing the water to slosh back and forth. This is the type of electricity that comes out of the wall outlets in your home. It's measured in volts. On to our final row. First up is the transistor. The transistor is arguably one of the most important inventions of the 20th century. It's the fundamental component that makes all modern computers and smartphones possible. At its core, a transistor acts as an electronically controlled switch or an amplifier. Think of it as a superfast, tiny water valve. A very small flow of water into a control pipe can open the valve and allow a much larger flow of water to pass through the main pipe. By using a small electrical signal to control a much larger one, a transistor can either switch the large signal completely on or off, or it can amplify the small signal, making it stronger. Next is the diode. A diode is like a one-way street for electricity. Its symbol is a triangle pointing towards a line. The current is allowed to flow in the direction the triangle is pointing, but it's blocked from flowing in the opposite direction. Imagine a one-way valve or a turnstile. You can go through it in one direction, but if you try to go back, the gate is locked. Diodes are essential for converting AC power to DC power and for protecting circuits. This next symbol is for ground. Ground is the common reference point in a circuit. It is defined as having 0 volts. Think of it like sea level when measuring the height of mountains. All other voltage measurements in the circuit are made relative to this ground point. So when we say a point is at plus 5 volts, we mean it's 5 volts higher than ground. It's also a critical safety feature. And finally, we have the switch. This one is the most straightforward of all. A switch simply opens or closes a circuit. Its symbol looks like a break in the wire with a little lever. When the switch is open, like a drawbridge that's up, there is a gap in the circuit, and no electricity can flow. When the switch is closed, the bridge is down, the path is complete, and electricity flows. A light switch on your wall is the perfect example. And there you have it. The resistor, inductor, capacitor, various power sources, and the key controllers like transistors, diodes, and switches. These are the fundamental building blocks of electronics. By understanding what each one does, you've taken the first and most important step towards understanding the magic happening inside all the devices we use every day. You've learned the alphabet, and now you can start to read the language of circuits. Thank you so much for watching. I hope you found this helpful. Be sure to explore more, stay curious, and maybe even try building a simple circuit of your own.